With a vision of providing quality education to students of various strata of the society, the founding stone of Tuljaram Chaturchand College, Baramati, were kept in the year 1962. The college has been formed with the efforts of numerous people.
Our society is a religious minority institute, and we thrive well with the preamble of Siddhir Nikantam, means knowledge from all the dimensions.
119 विद्यार्थ्यांना कॉलेज सुरू झालेलं. आज जवळजवळ 12,000 विद्यार्थी बसले. हे कॉलेज ग्रामीण भागातलं सगळ्यात मोठं कॉलेज म्हणून आज गणलं जात आहे.
The college is affiliated to Savitribai Phule Pune University.
We are willing to empower the youth to skill and career-oriented educational and vocational programs so that he will be full-fledged for grabbing the opportunities for his career.
The college has well-qualified team of experienced teaching staff who are always ready to help, assist, guide and motivate the students. Regular meetings are conducted to keep a track of the development of the students and to plan new activities for their growth. Providing various streams of education under one roof makes Tuljaram Chaturchand College a renowned academic institution. With such numerous courses being provided in the college, the administrative department continuously and promptly maintains a smooth flow of activities in a well-managed manner. The college focuses on imparting career-oriented quality education at par with global standard. The senior college offers 3 streams: arts, commerce and science. The college offers 22 different courses for graduation as well as post-graduation in various departments like Geography Department, Psychology Department, Yoga Department, Bachelor of Vocation Program of UGC in 2 disciplines, Food Processing and Post-Harvest Technology and Journalism and Mass Communication. The college has well-equipped laboratories where students under the guidance of their professors learn and conduct various experiments. The Electronics Department in the research arena. The Botany Department had set up their own botanical garden. Well-equipped biology labs. IT Department has well-equipped computer lab with Wi-Fi internet facility where students can develop their computer science skills. The classrooms are well designed with projection facilities and the students are encouraged to have better understanding of their subject with friendly interaction with the teachers. The college campus is built with a central library which has a huge setup of numerous books of various streams. Student can access the library and read on various subjects to gain an in-detail knowledge. There is a reading hall adjoined to the library where the students can peacefully study and take note on various topics of their interest. If a student wants to get some additional information on this subject, TC College also provides an internet cafe. The college has a huge auditorium, Jivraj Sabhagriha, with all the modern facilities where around the year numerous events and functions are conducted for cultural educational growth of the students. Along with academics, The college has given equal importance to physical development of the student by providing innumerable sports activities like volleyball for boys and girls, kabaddi, basketball, boxing for boys and girls. The college has trained and developed some great sports persons who have won remarkable awards on various national and international platforms. The college provides NCC training where the cadets are given basic military training in small arms and parades. The cadets are well trained and given preference over normal candidates during selections. The officers provide good training and disciplined education to the students. The NSS activities are conducted by the students like street plays to bring awareness in the society. Plantation, construction of bunds and many others. And for these activities, the college has received various recognition and awards for their contribution towards society. Since 41 years, the college has been organizing a Moropant elocution and debating competition every year, which is a state-level competition. The college publishes an annual magazine called Anekan to motivate the creative skills of our students by providing a platform where they can publish their poems, articles, and their opinions.
या संस्थेने प्रगती करत असताना आम्ही MBA कॉलेजची नवीन बिल्डिंग बनवतो. अनेकांत इंग्लिश मिडियम स्कूल म्हणून नवीन बिल्डिंग बांधून त्या ठिकाणी सुरुवात केली. या ग्रामीण भागामध्ये हे कॉलेज सुरू होत असताना इथल्या मुलींची निश्चितपणे एक चांगल्यापैकी व्यवस्था झाल्याशिवाय राहणार नाही. कारण सहसा मुली बाहेरगावी पाठवायला पालक तयार नसतात. पण हे कॉलेज सुरू झाले म्हणजे त्या मुलींना चांगल्या शिक्षणाचं दालन उपलब्ध करून देण्यासाठी होईल.
स्त्रियांच्या आरोग्यावर शिबिरं आयोजित केली जातात.
The college also fulfills its social responsibility by conducting various events of awareness and confidence building in women. And to build a healthy environment, it also conducts the activity of plantation. The institute has also received various government funds for its welfare and further development.
Our institute is NAC re-accredited with a B grade. Also, we have undergone ISO certification 9001. The college has received the funding for DST Physics program. The institute is recipient of Star College status from DBT.
The college has also got various funds like College with Potential for Excellence and has won many recognition and awards in various fields.
We are seeking that the student should be at the excellence at par, not only in academics but in other activities like sports, competitive career, as well as the vocational skills.
The teaching department over here is very much friendly. We have the library which includes books from all the streams.
We have achieved many prizes of national and state level.
The college has boosted our confidence. The computer science department of a college has well-equipped laboratory.
The teaching staff here is good at transforming student attitude and creating better individuals.
The days are not far ahead that this institute will be a benchmark not only in Maharashtra or India but at the global scenario.
This is the journey of Tuljaram Chaturchand College, where it has enriched and nurtured hidden talent of students from various strata of the society and transformed them into confident and responsible citizens to excel in all walks of life.
Welcome to all participants for third day first session of national webinar on trends and challenges in chemistry, organized by Department of Chemistry, Tuljaram Chaturchand Mahavidyalaya, Baramati. Today for first session we have with us Dr. Sudhir Arbuz. On behalf of my department, welcome you, sir, on this national webinar. It's my immense pleasure to introduce today's resource person, Dr. Sudhir Arbuz. Dr. Sudhir is working as a scientist at Center for Materials for Electronic Technology, that is CIMET, Pune, since 2008. He completed his master degree in 2002 in physical chemistry from Nauroji Wadia College, affiliated to Savitribai Phule Pune University, Pune. Dr. Sudhir completed PhD degree in Photocatalysis from the Department of Chemistry, Savitribai Phule Pune University, Pune. Dr. Sudhir also worked in National Chemical Laboratory, Pune, and Baba Atomic Research Center, Mumbai. His area of research is nanometal synthesis, photocatalysis, hybrid cell, solar cells, hydrogen storage, etc. Dr. Sudhir published about 70 research papers in international journals and attended several national and international conferences. He also served as a guest editor for American Scientific Publishers Journal. Dr. Sudhir is a young associate of Maharashtra Academy of Sciences. He has guided 2 PhD students, 1 MPhil student, and about 45 MSc students for their projects. With this brief introduction, I request to Dr. Sudhir to deliver your views on the topic synthesis of nanostructural materials and its application. Thank you.
Good morning to all of you. First of all, I would like to thank organizers for inviting me to deliver a lecture for this national webinar. I am going to talk on synthesis of nanostructured materials and its applications. Hope all of you are aware about the word nano. Nanometer means 10⁻⁹ meter. Am I audible to all of you? Okay. In my talk, I am going to speak about the CIMET, where I am working as a scientist. This is the outline of my presentation. I will first talk about the CIMET, then ongoing project activities at CIMET, then introduction to nanomaterials. Then I will be covering the applications of these nanomaterials in the various fields such as solar cells, photocatalysis, lithium-ion batteries, organic reactions, and antimicrobial coatings on various utilities used in the healthcare industries. CIMET is having 3 research centers: CIMET Pune Laboratory as well as headquarters, CIMET Hyderabad, and CIMET at Thrissur. Thrissur, it is in Kerala. Each center has its own mandate and defined working area related to development of materials for electronic industries and strategic sectors. At CIMET Pune, we are almost 125 people, containing scientists, PhD and project students, and admin finance staff. The CMET is Scientific Society, comes under the Ministry of Electronics and Information Technology, Government of India, New Delhi. At CMET, we are working in the various areas such as nanomaterials and devices, piezo-sensors and actuators, materials for renewable energy, ultra-high purity materials and integrated electronic packaging. Most of the projects received from Defense Research and Development Organization, BRNS, Department of Science and Technology, Ministry of Renewable Energy, and Ministry of Electronics and Information Technology. All these funding agencies we are having industry. Apart from this, we are having industry-sponsored projects also related to process development for nanomaterial synthesis. Okay, this is all about the CMET where I am getting my bread and butter. So now let us come to today's main topic, nanomaterial. The material having at least one dimension in the range of 1 to 100 nanometer is known as nanomaterial. But there is no such definition related to the size where one can say, yes, this is the nanomaterial. For example, 0.5 micrometer, one can also say it is 500 nanometer. Means, depending upon the applications, people are using word nano size or micron size. These nanomaterials are basic building blocks of nanotechnology. Each and every material has particular dimension, such as there are changes in surface, optical and transport properties. In general, the nanomaterials can be classified as 0 dimension, 1 dimension, 2 dimension, and 3 dimension. Depending on its size and shape. The 0 dimension are basically quantum dots having size in the range of 2 to 5 nanometer. 1 dimension material consists of rods and wires having diameter in nanometer scale and length can extend up to micrometers. 2 dimension materials are having plate-like structures, and 3 dimensions it consists of hierarchical morphology or hierarchical structure also. Let's see what are the properties showing changes when materials present in bulk form and transform into nanoform. Optical properties of the material is drastically changes due to change in the size of the material. The conductivity, melting point, surface properties, crystal shape, magnetic properties, chemical reactivity, and mechanical strength. All these properties shows different behavior while in bulk form and in nanoform. Due to changing the lowering of size or lowering the size, the surface area improves, which is beneficial for many applications. One such example is catalysis. In catalysis, if surface area improves, the catalytic activity of the material enhances. On the basis of the band gap of the material is classified as metals, semiconductors, and insulators. In case of metals, the valence band and conduction band are overlap on each other. So metals do not have any kind of band gap. In case of semiconductor, a maximum gap between valence and conduction band is up to 3.5 electron volt. And above this 3.5 electron volt, it is called as insulators. Do you know what is meant by band gap? It is just the energy difference between the top of the valence band to the bottom of the conduction band. In semiconductor physics, the band gap of semiconductor is always two types: direct band gap and indirect band gap. This figure shows the difference in the direct band gap and indirect band gap. In direct band gap, the electron from top of the valence band here directly goes to the conduction of low conduction band without changing the direction. Whereas in indirect semiconductor, the electron has to change its direction slightly. So this is a very simple explanation for keeping in mind the basic difference among the direct and indirect band gap. This particular question is mostly asked in the research-oriented recruitment interviews. Let's see how the change in the particle size changes the band gap. As the size of material getting towards nano size, the population of density of states quantizes, increasing the distance between top of the valence band and bottom of the conduction band. This increase in the band gap values results blue shift and also change in the color of the material occurs. For example, let's see cadmium telluride nanoparticles. It is shown here. It is having band gap of 1.5 electron volt. As the size reduces, the band increases up to 2.75 electron volt. So this is the bulk one, 1.5. If you decrease particle size, its band gap increases to 2.75 electron volt. As per the size of cadmium telluride, different colored cadmium telluride can be prepared. See the band gap and corresponding size of the cadmium telluride nanoparticles. Okay, now let's see the nanomaterial synthesis techniques. There are two approaches for synthesis of nanomaterial and the fabrication of nanostructured materials. First one is the top-down approach and second one is bottom-up approach. The top-down approach, name itself indicates slicing of bulk material to get nanoparticles. And this slicing can be done by various means. In case of bottom-up approach, the material is built up by atom or molecule by molecule to form the nanoparticles. These two methods, top-down and bottom-up approach, are having its own advantages and disadvantages. Advantages of top-down approach are large-scale production of nanomaterial is possible and chemical purification is not required at all. The disadvantage of this method is obtained particle size distribution is ranging from 10 to 1000 nanometer. The obtained particle have different shapes and size, and it could form the defective particles. And the major disadvantage is that it required costly instruments. As compared to this, the bottom-up approach is having advantages such as it gives ultra-fine nanoparticles, nanoshells, nanotubes, can be prepared easily, and it is a cost-effective technique. The main disadvantage of this method is large-scale production is not possible and chemical purification is required. Means we are using different capping agents or some reducing agents. We need to wash this material to get pure nanomaterial. These are few level methods for synthesis of various nanostructures. We at CMIT Pune Lab are routinely using these techniques. First one is the co-precipitation. It's very simple. Sol gel technique, hydrothermal and solothermal technique, combustion synthesis, microwave synthesis, sonochemical, and so on. Here also, each method have its own advantages and disadvantages. So depending upon the required properties of the materials, one has to choose the particular method. Sol gel method provide material with high porosity, resulting high surface area material. Hydrothermal and solothermal method gives us interesting hierarchical morphologies. We can able to make rods, plate-like structures, and hierarchical morphology using hydro as well as solothermal method. Combustion synthesis provide material with high crystallinity along with high surface area. The microwave synthesis technique provides us good quality material in minimum reaction time. So these are the specialty of each and every synthesis technique. Okay, now after preparing any kind of nanomaterial using the above earlier mentioned methods, one has to confirm the formation of particular material using some instrument. So these are some of the techniques can be used for characterization of the prepared materials. The UV visible spectroscopy used to find out the absorbance of the nanomaterial and band gap using Kubelka-Monk method. This is the basic instrument which can confirm the prepared material is nano or bulk, just looking at its surface plasma or absorption spectra. Photoluminescence spectroscopy provides us the information related to the formation of any kind of surface defect. FTR gave us the information related to the metal-oxygen bonding and metal capping interaction in case of nanomaterial synthesis. Or we can also check the purity of prepared nanomaterial, whether used capping agent is totally removed or still present on the surface of the nanomaterial. Scanning electron microscopy and transmission electron microscopy can be used to study the morphological and microstructure analysis of the material. The exact size of the nanomaterial can be seen from the DM analysis. Further, the thermal analysis provides the information related to thermal stability of the material, and it helps us to identify the evaluating gases with temperature and time if we couple this thermal analysis to the FTR. This is very important thermal analysis. We can get the information up to what temperature our material is stable and what are the changes can occur after certain temperature. Now we have seen the basic methods for synthesis and characterization. Now we will try to cover the applications of the prepared nanostructures, basically semiconductor nanostructure applications. The semiconductor nanostructure can be effectively used for various applications like solar cell fabrication, nanoelectronic devices, biological uses, sensors, clean energy production, organic synthesis, and environmental remediation. At CMET, we are making various semiconductor nanostructures and using that nanostructures for these applications. In this presentation, I am going to cover the solar cell application such as dye-sensitized and hybrid solar cell, environmental remediation, hydrogen generation via water splitting, organic synthesis, and biological application. Now, let's see the application of nanomaterial in solar cell fabrication. Let me tell you first what is meant by solar cell. As you must be known or seen solar cell, but its exact definition is solar cell is a device which converts light energy to electricity. Correct? Yes. Based on the material and the process used for solar cell fabrication, it is divided in 3 generations. First generation solar cell, it is used with single crystalline silicon as well as multi-junction solar cell. The second generation solar cell is based on thin film solar cell, made up of amorphous silicon or cadmium telluride or cadmium indium diacyanide. All these are in thin film solar cells. Third generation solar cell is about the solar cell which are in currently research phase. These are perovskite solar cell, dye-sensitized solar cell, hybrid solar cell, polymer solar cell, and quantum dot solar cell. Here, the cost of the solar cell is much decreases from first generation, second to third generation solar cell. Let's see now what are the components involved in the dye-sensitized solar cell. Here the schematic presentation of the different layers of the DSAC is shown. It requires photoanode, photosensitizer, electrolyte, counter electrolyte. Now see the details. The FTO coated glass is used as a conducting electrode. This one. The prepared semiconductor nanostructures use as a photoanode. It may be any kind of semiconductor, oxide or sulfide. Here I shown zinc oxide and diode. So it is coated on the FTO substrate. The dye molecules such as L719 dye adsorb on these semiconductor nanostructures. These are dye molecules which act as a photosensitizer. This is the important key part in the DSAC. And this is the iodide-based electrolyte to generate the electrons. And the platinum-coated FTO is another electrode for DSAC. So this is the schematic of dye-sensitized solar cell. So this is the typical picture of the fabricated DSAC at cement. So this color is due to the iodide electrolyte or somewhat due to the dye molecule. So let's see its general working mechanism. The dye molecule are excited by solar light absorption. Upon excitation, the dye molecule transfers its electron to the conduction band of semiconductor. And further this electron gets transferred to the load wire connected to the external circuit. Meanwhile, these dye molecules get the electron back from the iodide ion, and in this way the electricity gets generated. There are some specific equations and terms to calculate the solar efficiency. It is very important. The figure indicates the plot of current versus potential. The fill factor, maximum power, and in maximum power, this is the maximum power, and IPC means incident photon to current conversion efficiency. These 3 are very important parameters. The percent IPC is calculated using the ratio of number of electrons generated by number of incident electrons into 100. Using this equation, one can find out the solar cell efficiency. Another term is used PC, power conversion efficiency, to indicate the efficiency of solar cell. Here, we have prepared the TiO2 nanostructures using hydrothermal synthesis method and fabricated in solar cell. The XRD clearly indicates the formation of highly crystalline anodized phase of TiO2. This is the usable absorption spectroscopy. The DRS indicate the absorption age is around 387 nanometer, corresponds to the band gap of 3.2 electron volt. The APSM indicate the formation of uniformly distributed nanoparticles having size in the range of 50 to 100 nanometer. This is around 50 to 100 nanometer. This scale is 500 nanometer. Further, these particles are agglomerated to form micron-sized cluster and distorted spherical-like morphology. TM shows the presence of rectangular plate-like structure. The high-resolution TM image indicates the interplanar spacing of 0.35 nanometer corresponds to 1:1 HKL plane of anatase layout. The bright spot SAD pattern indicate the HKL plane matches with the anatase phase of T-iode. Here, obtained photovoltaic parameters are noted in this table. The maximum power conversion efficiency is 4.31 electron percent for the prepared diode nanostructure. This is almost double than the standard diode. This maximum is obtained due to the higher current density. Here we got the 9.26 milliampere per square meter current, which is almost double than the standard diode. This higher current density is due to the formation of nano-sized diode having better particle-to-particle linkage and maximum dye absorption due to nano size. Further, we have prepared the zinc oxide nanostructures at two different temperatures, with keeping all other parameters same. Only we change the temperature. Both the zinc oxide indicate the formation of hexagonal phase by X-ray analysis. The DRS shows the band gap values around 3.36 to 3.4 electron volt. It's almost equivalent. APSM indicate the formation of beaded nano chain network. Small particles agglomerated to form the nano chains. The Shedman sample with low reaction time have particle size around 10 to 30 nanometer, and in case of Shed2 sample, the nanoparticle size in the range of 20 to 30 nanometer. APTM analysis shows the nanochain bundles of particles are well connected to each other. It's well connected to each other. The fabricated DSAC shows higher efficiency for Z2 sample. Means this study clearly indicates the importance of reaction temperature for the nanomaterial synthesis. Now see the hybrid solar cell. Hybrid means use of organic polymers along with inorganic semiconductors. These are used to fabricate this kind of solar cell. So it is called hybrid solar cell. It's a mixture of organic as well as inorganic semiconductors. Advantages of these kind of solar cells are its active thickness is only 100 to 150 nanometer, and solution processing can be done. This cell consists of ITO coated glass as anode material. This ITO coated glass as anode material. Then this is the whole transport layer as a P dot PSS. Then mixture of organic and inorganic semiconductors, and then cathode. Yes, here we are using aluminum as a cathode. So here this is the general mechanism of this kind of solar cell. After absorption of the light, the polymer as well as semiconductor, both are get excited. The electron from the conduction band of higher value conduction band goes to the another electron, and this electron transport to the cathode. And in this way, the electron goes here, hole goes here, and this circuit is getting completed. So this is the whole process used for the fabrication of hybrid solar cell. First, the substrate is to be cleaned properly. First, it is cleaned by normal washing without detergent, then chemical washing, then ozone cleansing to remove all the VOCs what are adsorbed on the substrate, then coating of whole transport layer, then this coating of whole transport layer we use P dot PSS, then it is heated at 150 degrees centigrade to get homogeneous film, then active material coating, mixture of polymer semiconductor, inorganic semiconductor, then cathode deposition, then UV curing and testing of solar cell. So this is the whole process has to be carried out to fabricate the hybrid solar cell. Means here we have to do dual kind of work. Means we have to prepare the material, we have to characterize that material, then that material we have to utilize for device fabrication such as solar cell, and again we have to characterize that solar cell. Here at CMET we are fabricating hybrid solar cell based on cadmium sulfide as well as cadmium selenide nanostructures. So here we prepared the cadmium CDS nanoparticles using microwave synthesis technique. So UV visible absorption shows its absorption around 475 nanometer. The bulk cadmium sulfide showing absorption at 530 nanometer. So this particle is around 5 to 10 nanometer, so its absorption shifted to blue side. So 475 its absorption. Then PL emission gives emission at 520 nanometer. This emission is single emission. It indicates that this forms cadmium sulfide is diplet structure. XRD clearly indicates the formation of hexagonal cadmium sulfide nanostructure. The TM analysis clearly indicates slightly dumbbell-shaped cadmium sulfide nanostructures having size in the range of 5 to 20 nanometer. The d-spacing observed to be 0.316 nanometer corresponds to 101 plane of cadmium sulfide, which confirms the hexagonal shape of CDS. The SAD pattern also confirms the formation of polycrystalline nature. And here I have shown the IV characteristics of fabricated solar cell. So this is the IV characteristics. So we at present we are preparing this kind of solar cell regularly at CMET. Now next application of the prepared nanomaterials is photocatalysis. So let's see what is meant by photocatalysis. The photocatalysis is a catalytic reaction involving light absorption by catalyst or substrate. This is also known as advanced oxidative process. Can be effectively used for the complete mineralization of organic pollutants and degradation of various dyes present in air and aqueous system using invisible irradiation. Mineralization means any compound if you take, it's completely oxidized into CO2 and water. That's called mineralization. It's also known as photocatalysis, is also known as acceleration of photoreaction in presence of catalyst. But these catalysts are basically semiconductor oxides or sulfides. Basically, photocatalysis on semiconductor material is nothing but a redox reaction. Means at conduction band, reduction occurs, at valence band, oxidation occurs. That's why it is called redox reaction. For the first time, Fukushima and Honda in 1972 observed the water splitting over the TiO2 anode in presence of light. So what they observed, they prepared the photoanode of TiO2 and after shining the light, they found that at platinum electrode hydrogen generated and TiO2 electrode oxygen is generated. Since then, enormous amount of efforts have been taken all over the world by researchers to prepare highly active catalysts to generate the hydrogen, because hydrogen is very important for us. The hydrogen fuel cell or hydrogen is as fuel. It's very important for increasing population of the world. So let's see what is the general mechanism of photocatalysis. As I said that photocatalysis is basically semiconductor material. The semiconductor have band gap, valence band, conduction band. After shining the light with appropriate wavelength, the electron from valence band goes to the conduction band. And this electron in the conduction band reduces the H plus ions to generate hydrogen. Simultaneously at the valence band, the generated holes oxidize water molecule to get oxygen. In this way, by simply using sunlight and water and catalyst, one can generate hydrogen and oxygen. So these are the various applications of the photocatalysis. Water treatment, cell cleaning effect, air cleaning effect, for organic reactions, hydrogen generation, antibacterial effect, antifogging effect, and volatile organic compound degradations. In many countries, people have coated the semiconductor material on the wall side, roadside, and hospital tiles, so that in presence of room light, whatever the germs and fuses that can be oxidized. So what are the basic requirements for the material to be having good photocatalysis? First one is the catalyst should be chemically stable. Means during reaction it should not oxidize itself or reduce itself. It should have proper band gap. Band gap must be in between 1.7 electron volt to 3.2 electron volt. If band gap is lower or band gap is higher, then effective charge generation and separation cannot be taking place. The appropriate conduction and valence band potential. The conduction band level should be more negative than the hydrogen evolution potential. Then only one can generate hydrogen from the water splitting. And main is the effective charge separation of photo-generated electron hole pairs. If this separation is not effective, then these electron holes again recombine and one photon is being lost. So whatever the changes is occurring, people are trying for effective charge separation. So how the effective charge separation can be done? One is that loading of these noble metals on the surface of semiconductor. And this platinum, palladium, ruthenium and rhodium is having higher electron affinity, and due to this higher electron affinity, as soon as the electron hole pair forms, it easily captures the electron and give for further reaction. So using this co-catalyst, one can increase the hydrogen evolution rate by 2 to 100 times. So here at CMET, generally we are using platinum as it is having higher electron affinity, and its amount is just negligible, 0.01%. So this is the general setup at CMET. So this is the mercury vapor lamp. It is fixed in the water jacket. This lamp is also emitting ion radiation. So due to that, the heating effect is being occurred. So to absorb the ion radiation, we are circulating water in this. So this round bottom flask contains our prepared catalyst plus water. And after starting this lamp, whatever this hydrogen, oxygen is coming out, it is being collected through this pipe in this modified heliometer tube. And this heliometer tube, its water is filled. This is the water, and with as the gas comes, it is going up. With time, we can monitor how much hydrogen and oxygen is being collected. And here it is septum arrangement. Using gas type syringe, we can take out the gas and we can analyze the amount of hydrogen and oxygen using GC fitted and equipped with high angstrom molecular fuse column and thermal conductivity detector. So this is the setup for dye degradation or any organic or inorganic pollutant degradation. Instead of round bottom flask, here is we can keep bigger or conical flask, whatever material you have to keep it here, and with time just monitor its degradation. And this analyzes this degradation with the help of usable spectroscopy. If you have gas chromatogram, you can analyze this on gas chromatograph also. So this is the general spectra of the methylene blue dye degradation. In India, we have many textile industries and they are using number of dyes for dyeing the fabrics. And whatever, they are not taking care of the pollutants. They are directly emitting this colored waste into our ecosystem. So this can be treated using our solar light photocatalysis. So this is the methylene blue. We have taken its 10 ppm solution. Its absorption is around 1.6. As we irradiated this in presence of our photocatalyst under sunlight, with time this absorbance is getting down. So within 2 hours the absorbance is totally zero. Means it shows complete mineralization of this material. Now let's see the synthesis of zinc oxide nanostructures. This is the very basic thing I am telling. This is as many of the participants are students. So how to prepare zinc oxide nanostructures? So here I have taken the zinc nitrate and sodium hydroxide, and I am using here EDTA, ethylene dimethyl acetic acid, as a capping agent. So this plays an important role in governing the morphology of zinc oxide that to be going to form. The separate solution is mixed, transferred this into this Teflon container, and this container fitted into hydrothermal reactor. It is being sealed and kept in oven for 200 degree. The time is varied 2 hour, 4 hour, 8 hour, 12 hour, just to see what is the influence of temperature on the obtained product. So let's see. This is the XRD analysis of the prepared zinc oxide. Only here we did 4 type of reactions. Only the time is varied. Other parameters are same. So in all 4 compositions, the zinc oxide shows formation of highly crystalline hexagonal phase of TiO2. The usable absorption spectroscopy also shows the absorption at 380 nanometer, and it is same for all the prepared compositions. Only as time increases, the peak height is getting decreases. This is the SEM analysis of the prepared zinc oxide. So see, here we are getting uniformly hexagonal shaped zinc oxide plates having size in the range of 50 to 100 nanometer. So this is for 2 hours. As we increase the time to 4 hours, 8 hours and 12 hours, see how the morphology getting changes. This plate slightly getting growth direction in Z direction, then it is becoming circular, and this is the 3D structure. So this 2 dimension becomes 3 dimension. So this is the impact of time. So we also evaluated its photocatalytic performance. This is the schematic of our degradation setup. Already we have seen in earlier slide the actual photograph setup. So it contains quartz condenser, water inlet, mercury vapor lamp, water outlet, dye solution, and magnetic struggle. So this is the degradation results. So whatever we prepared, the zinc oxide at 8 hours shows highest rate for the degradation. So almost in 2 hours it completely degrades the 10 ppm methylene dye. So the reactivity trend observed are 8 hours is having higher reactivity, 12 hours, then 2 hours and 4 hours. Another, we prepared the titanium dioxide using solar gel technique, and here also what we did, we heated this TiO2 at 400 degree, 500 degree, 600, 700 and 800 degrees centigrade. This heating temperature we are observing or decided by the thermodynamic analysis of the prepared TiO2. So the TiO2 prepared at 400 nanometer, 400 degrees centigrade is showing broad XRD peak. Broad XRD peak indicates the formation of nanosize. After heating, the size getting reduced. Size is increasing, and at 600 degrees centigrade, the peak at 27, 2 theta 27 starts appearing. At 700, the peak at 227 is higher, and the peak at 25 is lower. And at 800 degrees centigrade, the peak at 27 degrees is higher. What it indicates? It indicates that TiO2 is here up to it is anatase phase. For A and B is anatase, means up to 400 and 500 degrees centigrade, it is anatase phase. Then at 600, the anatics phase starts converting to rutile phase. At 700, almost rutile is 90%, anatics 10%, and at higher temperature 800, only formation of rutile phase observed. Means that we can, from this study, we can judge that up to 600 anatics phase is stable, and above that rutile phase starts existing. This is the DR spectra of this material. See, the anatics phase is having band gap around 3.2 electron volt and rutile is around 3 electron volt. This is the tau plot to give clear picture of band gap energy. This is the TM micrographs. So here fine particles agglomerated to form some 200 nanometer crystals. So here particles are getting larger and here plate-like structure is being observed. So this is just as we heat the material, they are getting much energy and small particles diffuse together to form larger particles. We also evaluated its photovoltaic activity to generate hydrogen. So here we observe that the material prepared at 400 degrees centigrade is showing highest hydrogen generation, almost 1200 micromoles per 0.1 gram per 4 hour. As this is particle size is much narrow nano size, that's why it is giving us higher particle size, higher hydrogen generation. And the TiO2 prepared at 800 is almost 200, means TiO2 prepared at 400 degrees centigrade shows 6 times enhanced hydrogen generation as compared to TiO2 prepared at 800 degrees centigrade. From this study we can fix that we have to prepare TiO2 at 400 only so that it can give maximum hydrogen. Now other people are trying that the TiO2 its band gap is 3.2 electron volt, means it's required 400 nanometer light, and in our solar light 400 nanometer light is only 4 to 5%. In order to effectively utilization of solar cell, visible portion of solar cell, that is 35 to 40% available, that we can utilize if we shift the band gap of TiO2 from 3.2 to lower side like 2.4, so that we can use its visible portion of the solar light around 400 to 600 or 700 nanometer. So in this regard, what we did, we doped vanadium in TiO2 ranging from 0.1 volts mole percent to 20 mole percent. So in this case, what we observed, other parameter kept constant with 0.1, 0.2%, 4%, 10 and 20%. So in this case, what we observed, nanoparticles are getting rod-like structures and then aggregated to form larger structures. So this change in the morphology is due to the increase in the concentration of vanadium. Also, one more effect we observed that as we increase in the vanadium concentration, the stability of anatics phase gating decreases. The anatics phase getting transformed completely into rutile phase, above 4 mole percent doping of vanadium. But advantage is that the vanadium is having just lower conduction band level than the TiO2 band level. That's why the band gap is decreases, so that we can utilize the solar light. So this is the band gap of vanadium doped TiO2 nanostructure. This is the pure TiO2 and this is the vanadium doped TiO2. Means this much portion of solar light we can use. Further, we prepared the tungsten oxide nanostructures. Here also we heated these tungsten oxide nanostructures from 200 to 800 degrees centigrade to find out what is the effect is being occurred. So here what we observed at 200 degrees centigrade, we are getting nice belt-like structures. Further heating, this belt-like structure is formulated into spherical particles. It's well connected, and after that it agglomerated in the irregular shaped material with higher particle size. Further, we prepared the zinc oxide nanostructure with different capping agent. In earlier slide, I have used ethylene diamide tetraestic acid. Here, I use EDA, ethylene diamide, only as a capping agent. And this being other parameters, same only reaction temperatures vary from 2 hours to 48 hours. So here what I observed, here the length of the rods are smaller. With time, the length of the rod is getting increases. And at 48 hours, the length of the rod is almost in micron size. But diameter is same. Diameter is almost 50 to 100 nanometer. Here, the PL spectroscopy, we are getting good results in PL spectroscopy. As the reaction time increases, we are getting this additional emission peak at 500 nanometer. So this is the bandage emission. Means when the electron goes from valence band to the conduction band, and again it is coming to the from conduction band to valence band, at that time it emits the light. So this is the light at 390, and this is further due to the defect. As we increase this reaction temperature, we are getting additional green emission band at 500 nanometer, and this is very good kind of material that can be used for fabricating green light LEDs. This is the TM analysis of the rod. This is the pencil-shaped tip-like structure is getting observed. This is the invisible spectroscopy. It shows the absorption at 372 nanometer. And this is the schematic presentation of the facets available with the prepared zinc oxide nanostructures. Further, as I mentioned, the loading of noble metals or transition metals on the surface of zinc oxide increases the photovoltaic activity. In this regard, what we did, we prepared pure zinc oxide nanorods. On that, we loaded 0.5 to 10 more % zinc oxide. This is exciting pattern. So here up to after 1 mole %, we are getting peak for silver, metallic silver nanomaterial. So X-ray clearly indicates the presence of silver along with zinc oxide nanostructure. And we observe this photovoltaic activity. So what we observe that as we increase the percentage of silver, we are getting higher photovoltaic activity for dye degradation. Almost in 1 hour, it completely degrades the dye. See, for zinc oxide, its activity is lower. For point, as we increase the silver percentage, the activity is getting increases. So this is the general mechanism why this activity is increases. Because as soon as the electron hole generated, this electron getting absorbed by silver and it is processed for further degradation reaction. We are also finding its rate constant values. Means for chemicals kinetic study by plotting ln C0 by Ct versus time. So we are getting the chemical kinetic rate constant for 10 mole % silver zetron is almost 6.01 into 10 raised to minus 2. This is almost 6 times more than the pure zinc oxide. See, the reaction rate getting 6 times faster as compared to pure one. Then we tried a coupled photocatalytic system. Earlier we were using one photocatalyst only. Here we are trying coupled catalytic system. Serious data. This will prepare zinc oxide rods. On that, we institute from the cadmium sulfide nanoparticles ranging from 0.1 mole % to 5 mole %. So this is the zinc oxide rod, and whatever the spherical particles, it is of cadmium sulfide. This is the uniformity of formation of zinc oxide rods, and this whatever white spot, that is cadmium sulfide. So we observed that 5 mole % serious loaded zinc oxide giving highest hydrogen generation over the zinc oxide. Zinc oxide is pure, not showing good photocatalysis activity for hydrogen generation. But for dye degradation, there is good activity. To enhance this activity, you loaded CDS. CDS improves its catalytic activity. It's from 300 micromole per 0.1 gram to almost 650 micromoles per gram hydrogen we are getting. This is the general mechanism. Why this is happening? Why we are getting enhanced hydrogen over CDH? Because this is the mechanism. What is happening? Both the electron semiconductors absorb light, generates electron hole pairs. But what is happening? Within the electron, this electron hole again recombining, so that we are losing our absorbed photon. But in case of coupled semiconductor, what is happening? As soon as the electron generated, this electron and this hole get recombined, so that we are getting this electron for hydrogen generation. So one we are bearing and one we are utilizing. In this way, the activity of photocatalyst can be enhanced. So just see what is the general mechanism of coupled semiconductor system. This is zinc oxide, this is cadmium sulfide, this is the energy levels with respect to the vacuum. After shining the light, the electron from alkaline goes to the conduction band, and these electrons are recombining, and this is the sacrificial reagent we are using. So it traps the hole, it oxidates methanol to get CO2, so that this electron is free for generating hydrogen. Okay, the similar coupled semiconductor, we prepared cadmium sulfide. Now here we are preparing PQ diode. PQ means pentazinc, It's well-known organic semiconductor. We prepared this PQ diode compositions from 0.01 to 0.21%. So this is the rod-like structure and particles. This is what your rod-like structures is of PQ, and these are the TiO2 particles. So here also we observed that the PQ with 0.2 mole% loading is having higher photocatalytic activity as compared to pure one. So this is general mechanism, same as we discussed earlier. Then again, we prepared the cadmium sulfide nanorod and nanowires. For this purpose, we use ethylene diamide as a capping agent. And this is ED is very beautiful chemical. It is structure directing agent. So at 12, what we did the same reaction, we kept at 12 hours and one kept at 48 hours. In both the cases, we got the rod. This length of rod is lower, up to 200 nanometer. But here, the length of the rod is drastically increases. Its length is up to 5 micrometer. And from XRD also, we came to the 002 peak intensity is higher. Means here, we can say that the rod length is higher, lower. But as soon as this peak intensity getting lower, means we can say that there are some specific orientation has been occurred. From looking at XRD spectra, we can judge we have some different kind of morphology. We also prepared SNS2 nanosheets. So SNS2 is band gap is around almost 2.4 electron volt, which is equivalent to cadmium sulfide nanostructures. We prepared this cadmium sulfide nanostructures hydrothermally. This is the DRS spectra. Its band gap is around 2.4 electron volt. This is the general formation mechanism we discussed. This is same spectra, and this is TM. It's clear benzene structure. This hexagonal plates agglomerated in such a way that the rose-like morphology will form. And this is the degradation spectra for this material. Okay, now we discuss applications such as solar cells, then photocatalysis, and now this is the third application we are going to see, lithium and batteries. Let me tell you something. So, at CMED, we have established a center of excellence in lithium and battery, fully funded by Ministry of Electronics and Information Technology. This is the first kind of laboratory in India dedicated for lithium and battery fabrication as well as research. Here, my colleagues, Dr. Milind Kulkarni, Dr. Kale, Director and Director General of CMED, working on the lithium ion battery. Their group fabricating anode, cathode, and fabricating different kind of lithium ion batteries, such as button cell, pouch cell. Very recently, CMED prepared the battery for two-wheeler, e-vehicle, and successfully demonstrated its functioning in running the two-wheeler. It has huge market in the battery. At present, the lithium-ion battery all we are importing from the China. We have lithium-ion batteries in many gadgets. Small gadgets means now whatever rechargeable gadgets we are using, that is all our lithium-ion batteries. Cylindrical cell, pouch cell, button cell. There is huge market. Basically, everyone is having mobile, so its battery is almost 5 ampere hour or 5000 milliampere hour. You just see your battery of moped, Activa or any button start motor, is lead acid battery. See the size of that battery and see your mobile battery. The capacity is same, but size is different as well as weight. So that's why lithium-ion battery is very important for the e-vehicles. What is happening in primary batteries? The electrical reaction is not reversible, non-rechargeable. So therefore, it is need to develop these lithium-ion batteries. And apart from lithium, there's sodium and magnesium, which are the active material for these batteries. So this is the general charging discharging mechanism of the lithium-ion batteries, what exactly happening during charging as well as discharging. So lithium ion here, just for the sake of research, I have shown the lithium ion battery and sodium ion battery. The lithium ion battery is lightest and excellent electrochemical activity, high energy and power densities, good Coulombic efficiency even for leaking. This leaking is observing. You might have seen sometimes while charging the battery getting explode. Disadvantage is that expensive protection from being overcharged, super self-discharge, still questionable for using e-vehicles, but still there is no alternative. Hence, new material development need to be continued for LIPs. At CMED, we and our colleagues, what we are doing, we are just developing different kind of anodes and cathodes, which are compatible and solve this kind of disadvantages. Alternative batteries are sodium-ion batteries. It is cheap, abundant, and source of sodium is also put in India. Charging faster, deliver more energy quickly, completely drain without damaging the active material. Potential for grid-scale application. The size problem is size of sodium ion larger than lithium ion. Still need to be work on market for stable performance for alternative to LIS. Further, it required further study as well as modification. So these are the parts. You might have wondered, whatever the button say you are using your watch or some cells, it contains almost 7 to 8 parts. What are the steps involved in cell fabrication? First process is synthesis of anode material. After synthesis, one has to characterize this material with XRD, APSM, HRDM, XPS, Raman. Step 2, electrode fabrication. The material preparation by ball milling, mixing, vacuum, then electrode sheet preparation such as coating on copper foil, whatever material is being prepared is need to coat it on copper foil, then roll place for uniform thickness and disc cutting. Whatever you are coating the material on copper, it will be coated in disc format so that it can fit here. Then assembly of the lithium-ion battery cell, sealing of the cell in glow box. The glow box means that you have to fix the environment, oxygen-free environment in that, so that the active material should not oxidize, electrolyte injection and crimping. Then step 4 is cell testing. After fabricating, one has to test the cell whether it is working or not. Cyclic voltammetry by our impedance analysis. It's being characterized by a specific capacity, rate capacity, capability, Coulombic efficiency, and cyclability. It's almost 1,000 cycle charging and discharging. It has to be passed so that one can use. Everyone mobile charging at least once in a daily. It's one cycle charging and discharging. If you continue to 1,000 means that battery can work up to 3 years. This is the equipment at CMED Pune. This is the ball milling where the material is being mixed. This is the mixture and coater. This is the vacuum or drying. This is the roll press. This is the sealing cutter. And this is the blow box. It contains oxygen-free environment. Here the electrolyte is being added and cell is being sealed, and this is the battery testing unit. So these are the various cells kept here for testing, pouch cell as well as button cells or cylindrical cells. Now fourth application of this nanomaterial we are going to see is for conducting the organic reactions in the catalysis. One example I have given here is Hague reaction. Hague reaction is very famous. Hague reaction is nothing but the carbon-carbon bond formation between aryl halides and olefins. And this reaction carried out homogeneously as well as heterogeneously. Earlier, the Hague reaction is being carried out by 1 to 5% palladium along with phosphine ligand in presence of suitable bases. But this homogeneous reaction the traces of this metal will remain in the material. It's very tedious job to purify it. So it is better to use heterogeneous catalytic system. So here we developed TiO2 nanostructure, we loaded palladium on that, and we use this system heterolytically to make carbon-carbon coupling reaction. So this is iodobenzene and it's been reacted with this aniline and we get trans-ethylcinamate as well as cis-ethylcinamate. So here I'm going to see here this TM analysis of the prevalent catalyst. So this is the TiO2 material. Its size is around 100 to 200 nanometer. And whatever small spots are being seen, that is the palladium, its size is around 2 to 4 nanometers. See, this is the high resolution TM image. This is the one spot, it's being enlarged. And see, this is the interlattice passing. It confirms the formation of palladium nanoparticle. This is the catalyst before the reaction, and this is the recovered catalyst. See, means palladium is again on this TiO2, again recovered. We can say that this is recycled. Successfully recycle the catalyst for further reaction. Okay, for the last use of our nanomaterial technology, being a scientist, it's our responsibility to invent some products useful for human being. And from last 10 to 12 months, we are facing the problem of COVID-19 pandemic situation. So we decided to prepare some nanomaterial based coatings. So as we all know that nanomaterial is having antibacterial, antimicrobial effect. But how to use it? So what we did, we developed some silver based nanomaterials and we mix it with some polymer material and spray coated on these fabrics. And this, we tested its microbial activity against bacillus bacteria as well as S. aureus. So it's giving good activity. And as in presence of light, its efficiency is almost enhanced by 10%. So we developed such coatings for nanomaterials, and this being used and distributed. Almost we have coated 200 masks and distributed among the frontline workers. So I am at the end of my presentation. So the students have opportunity to work at CMET. We are taking BSc, MSc student with specialization in physics, chemistry and electronic science. Then B in chemical metallurgy and ANTC, MTech in nanotechnology. We are hiring these students for various projects. The PhDs in physics, chemistry and electronics. We have 27 PhD students registered at CMET Pune, affiliated to Savitribai Phule Pune University. We regularly recruit project staff, junior research fellows and research associates. For more detail, you see our website and we'll be happy to allow you to work at CMET. Thank you.
Thank you, Dr. Sudhir sir, for giving such a wonderful and informative lecture on the synthesis of nanomaterials and their applications. This lecture will be helpful for the participants and researchers while doing their research. Once again, on the behalf of my department and organizing committee, I am very thankful you, sir. Thank you. Now I request Dr. Bhandwe to take the today's second session charge. Thank you.
Good afternoon, everyone. This is our third day of national level webinar on trends and challenges in chemistry. Friends, myself Dr. Rahul Bhandwe, and I am here to welcome our today's guest, Dr. Bhalchandra Kakade. Dr. Kakade is now working as Associate Professor in SRM Research Institute, Chennai. He worked as a postdoctoral researcher in Tokyo Institute of Technology from 2008 to 2012. Before that, he was a doctoral degree student in National Chemical Laboratory, Pune from 2003 to 2008. His research work is primarily focused on low temperature fuel cells, especially oxygen reduction reactions, and also he's working on methanol electro-oxidation, catalytic corrosion and durability, composite polychlorides, double lead hydroxides, noble metal-free materials, and friends, he's also working on CO and CO2 conversion. So there are so many research areas he's exploring. He's very dynamic and he have 70 research papers as well as 7 patents on his credit. Friends, he is guiding 7 PhD students and also have 3 sub-funded projects as well as 1 industry-funded project for his research. So I welcome Dr. Kakade and I request him to start his lecture for our students. Thank you very much.
Thank you very much. First of all, for inviting me for this 3 days national webinar on trends and challenges in chemistry by Tuljaram Chaturchand College, Baramati. I especially thank convener Brunga sir and coordinator Yogesh Indulkar for inviting me for this webinar. Hope the audience of this webinar is master student and some of PhD students. So I'm going to present few important studies or understandings of fuel cell catalysis, how the electrochemistry works in this direction, how electrocatalysis in low temperature fuel cell works, and their fundamentals and applications. So I'm basically Dr. Balchandra Kakade from SRM Institute of Science and Technology. I'm working here for 8 years after coming from the Tokyo Institute of Technology. So before going to the details, I would like to thank first of all my students. Those are working very hard and they are doing several experiments, and because of that only I'm here to present you some recent studies. All these are my students. They are working day and night, as some of my students have been graduated and located in different places. Some postdocs also worked with me, and of course I should thank funding agencies like Research SRM Institute of Science and Technology, DST-SCRB, YSS, DST-SCRB, AMR, MNRE, Government of India, and Titan Phoenix for industrial project. So apart from that, I should thank all my collaborators, foreign collaborators, Indian collaborators for their immense support and help. Now, I should give an outline of my talk. What is today's recipe about my presentation? In the introduction, I will be talking about the energy conversion and how fuel cells are very important. What is a fuel cell basically? And what are the current progress in the fuel cell technology? And the basic sciences, what we have done in our laboratories. Especially we are expertise in oxygen reduction reaction, is electrochemical reduction reaction, and how the platinum alloys plays an important role in such reactions. What is this ORR, oxygen reduction reactions? And eventually I will end with the stability and importance of the stability in during the technology transfer and so on. And finally I will take up few of your queries and discussion. So before going to details, the one question, so we should realize what is research and how to kickstart any problem. So whenever there is a problem, we should know the solution. That is how the research. So before we go into a solution, what is the problem? So we have to discuss about the problem, whether we can go to the solution. So these are the 2 points where starts the problem and we end up with the solution. So before starting a solution or finding a solution, we should ask 4 questions. Out of that is first, why? Why we are doing this? Is it really necessary? And is it really important whether we should go for that or not? So these all questions we should, first question we should ask is why. Why this is important, whether it is important. Second one, whether it is interesting or boring. This problem is really interesting, then it is worth to go ahead. Especially these graduate students who are listening this presentation, they should realize that when now they are entering into the research, so they should realize any problem they are going to start or they're going to solve it, they should find out whether it is interesting or the boring. Second, whether it is a cutting edge. Cutting edge means whether it is a hot topic, whether it is a required, whether it is required for the social need, whether it is required for the national need. It is a cutting edge. It means it's a very frontier problem. So whether it's a frontier problem or cutting edge problem, and eventually we should know whether whatever you are giving a solution, is it a new, whether you are going providing a new solution for this. These questions, all problems once you solve, why, whether it is interesting and it is a new, and are you going to give a new solutions, then the rest of the problems are solved. That's it. You have solved the problem. So this is how overall, process of a research. When you're starting from a problem and giving a solution, then first 4 basic questions you should ask to yourself: why I'm choosing this? Second one, whether it is interesting to me. Third one, is it a new one? And finally, whether whatever you are going a solution, is it a new? Are you giving a new solution or not? So that's all. That's it. You are going to solve the problem overall. Now, then I will start with the very daunting challenge of the humanities in next 50 years. Then once you realize that what are these daunting challenges, you can see that all these points, starting from the energy, water, food, environment, poverty, terrorism and war, disease, education and populations, all these problems are very big problems among themselves. So these are not small problems. All these problems are quite big. And at least, it is our responsibility to contribute in this direction to solve these problems in the next 50 years. You can see that one by one. All these are distinct problems we are going to face in our few generations. So this figure shows that this whole universe or the earth is in our hand. It is us. We are going to change the world. We are going to change the universe. It is in our hand by solving all these daunting challenges. So I'm not going to touch everything, but my challenge I'm going to choose is the energy, how I'm going to contribute for the energy and so on. So if you look at the energy part, so current scenario here that we are putting a flame in the both direction of the earth, so that we are melting the both sides of the earth, like ice is getting melted. So this is a very familiar picture. Everybody, all of us, we are very aware of that first picture of a mother is cooking on a chula. The fuel is basically the wood and so on. So earlier days, the women used to cook their food by using the wood, which was the fuel people used to use. Then later on, it moved with the farms and so much like agriculture evolution. We started with the gobar gas. We started cooking and burning this cooking gases like gobar gas we used to call. Then we slowly moved to the LPGs. Where people started when we are using this LPG. Then you can see that trend. Well, nowadays we are completely dependent on the microwaves, the induction cooking, and so on. So you can see the train starting with the wood, then cow dung, then LPG, then slowly we are entering with the electricity. It means that wood or cow dung in 80s and so on, we started with this wood, then we are now in the electricity era. So we cannot live without electricity. The electricity makes an unavoidable part of our life. So you can imagine that for some time, for certain time, our phone is uncharged. We cannot live without the phone. So it means that the electricity is very, very important for current era. So how to solve this? See, the electricity, everything is dependent on like fossil fuels. Everything is fossil fuel. So this slide makes very important to understand it that. So it is something of an uncomfortable fact that the civilized society is almost completely reliant upon fossil fuels. You can see that whatever we are doing and what we have done, all the changes, what we are seeing, everything is dependent upon the fossil fuels, like petroleum, gas and everything. These are the fossil fuels. These are generated by how the fossil fuels have been formed. Our planet gets most of its power from the coal, oil and the gas. So these so-called fossil fuels were formed from the remains of living organisms existing millions of years ago, and when burned, release heat energy that can be turned into the electricity. So millions of years, these all living organisms are buried below, and then we get the oils and several forms of the fossil fuels. So, however, they are also very harmful to the environment, as burning fossil fuels also gives off a lot of carbon dioxide, a greenhouse gas we call, and that contributes to the global warming. You can see that in USA, it is the largest coal reservoir in the USA, and followed by the China and Russia. The oil reservoir is Venezuela is the largest one, and which is followed by the Middle East and the Canada. Now we can see that this gas reserves, the country with the largest natural gas reserve is Iran. So we have Iran, Russia, Qatar is full of the gas reservoirs. But what is happening? The thing is that in approximately 250 years, this all the coal is going to be finished. So it is going to be extinct. Like we are not going to get coal. Then gas supplies are next 70 years we can rely upon. After that, what will happen? Then other problems, because of this burning up oils and gases and so on, we are evolving so much CO2. How this CO2 is forming? We know that as sun's energy beats down to the earth, approximately 70% of it gets absorbed by the land and oceans, while 30% is reflected back, right? We are giving back into the space. However, 70% absorbed by the earth, eventually radiated back out into the atmosphere in the form of infrared energy. Greenhouse gases then absorb this energy, but also emit heat in the process, which warm the Earth's surface and lower atmosphere. This process occurs naturally and is what keeps the planet warm, right? This is what planet become warm, and which is enough for living things to survive on it. That is how we are getting a heat, because of the 70% heat is reflected back into the atmosphere, and the greenhouse gases absorb this energy and they are warming the atmosphere. This is the greenhouse effect, right? So what happens is this dramatic increase in the greenhouse gas emissions since the Industrial Revolution has also caused a big rise in the average surface temperature of the Earth. So this every year, every decade, we are getting an increase in the average temperature of the Earth, right? So what is happening? What is the consequences? We are getting a sea level increase, right? We are getting extreme weather conditions, like we have so many places we have droughts, so many places the flooding, hurricanes. We are experiencing that, right? In India as well, we are experiencing this. So one has to find out these examples, right? We can see that this in turn has caused the world's glaciers and ice shelters to melt faster. These ice shelters are getting melting very, very fast, which will lead to the rise in the sea levels, resulting in flooding of low-lying areas of coast. Many places of India and the world, like the main cities like New York, Mumbai, Tokyo, they are under threat, right? Once the sea level is increasing, ultimately after a few years, they will sink into the flood or in the water, because we are melting the glaciers in both the sides. Because of the global warming, the average temperature is getting increased, right? Apparently, we are witnessing an increase in the global temperature that adds some fierce and devastating tropical storms and hurricanes, and could also trigger severe drops in many parts of the world. We are getting these all, these examples are very, very, we are facing this day-to-day life. This is the capital of India, Delhi. You can see that, fog is a smog. What is smog is a mixture of the fog as well as the particulate particles. They are making, poisonous atmosphere in, you cannot enter into the Delhi. This is a very horrible condition in Delhi in the winter especially. This is, 3 years back, we had a flood in the Chennai. You can see that many people came into on the road. And apart from that, we are getting a toxic air. Globally, we know that this is the old data, 2015. Then I'm sure that this data has become much more distinct, and the condition might have been worsened further. So global air pollution caused more than 4.2 million premature deaths in 2015. So you can think about 2021. What should be this number? It could be very, very high. So as many as 92% of the world's population lives in areas with unhealthy airs. This is a very, very challenge and daunting for us, right? So one has to think about how to reduce these particulates, how to reduce this smog into the atmosphere, how to reduce the CO2 and other, once we are facing this all unhealthy air, then what is the consequence? We have different diseases like high blood pressure, smoking, high fasting plasma glucose, high total cholesterol, ambient particulate matter, air pollution, and we have COPD kind of disease and so on. So all these are the daunting challenges because of burning of fuel, fossil fuels. So after this, we have to think about the real green, whether what we are doing is a green or not. We have to think about. This is one of the finest example. Recently, what we have seen that if you go for the November 2019, the capital city was looking like a smoggy, completely smoggy. The next person you cannot see after 10 feet. So within just the 3 to 4 months. This is 30th of March of 2020 where we have a complete lockdown. Complete lockdown means there was no person on the road. It means that we are not burning the fuel, we are not having any automobiles, nothing else. So you can see that atmosphere becomes very clean. So what is the consequences? The nature itself is responding, right? The man is polluting the atmosphere, but here, the nature is responding that, okay, enough. The human enough, then let me wipe out this. Now you have seen that last 8-9 months we are inside the home. We were like jailed, but to create the clean atmosphere. This is how the nature can respond if the human are working against nature. So this is a very, very important, figure and clarification within the 4 months in the capital city of India. So one has to think about what to do the next. We have to think about the green. So one of the, another finest example of the Google search engine. Now everybody knows that the Google is the largest, search engine, which processes nearly 13 billion monthly searches. So it is very huge. And these kind of, all searches have been done because of the huge number of the data centers and with thousands of servers capable of doing all these works in a Google. So I'm not going into more details, but just see that how we are consuming energy and how that energy in a Google search, we are evolving CO2. So if you click once, right? We are clicking so many times in a day. Now everybody is, having the smartphones and so on. So if you click one in a Google search, you can consume this much energy, 0.003 kilowatt hour. So to generate this much of the energy, how much CO2 has been burned? You can see that 0.02 grams of the CO2. It looks very small when it is a single click, right? But if you see the all monthly Google searches, that all monthly Google searches gives you 3900000 kilowatt hour, and it contributes almost 260,000 kilograms of the CO2 into the atmosphere. So you see that this much, in a 1 month, this much of the CO2 is evolved out just by Google. You might ask why clicking the Google will. So it's an indirect, connection that this much energy to generate this much data will work. You need this much energy, and how to create this energy after burning up this much CO2, right? Then we can see that how much energy. So if you take an example of a cycle, to power this cycle for 1 monthly Google searches, it can run up to almost 6,000 years cycle. This much power is required. For example, it can power 100-watt bulb for almost 4,500 years. So this is very quite high. 30 days. In 30 days, this much energy we are consuming and this much amount of the CO2 we are evolving out into the atmosphere. Isn't it a very, very challenging and very scary scenario? So this is what the consequences of what we are doing, what we are contributing into the atmosphere. CO2 is at 407 ppm, by October 2018 increased by 90 ppm in last 70 years. Global warming, of course, increasing 1.1 degree in the past 200 years. Acidic ocean acidification is happening. There is increase in the sea level, almost 3 to 4 mm each year. Decreasing ice melts, ice sheets mass, retreating glaciers, decreasing Arctic ice at the rate of 13% each decade, which is very huge, right? That's why inch by inch, Mumbai, New York, all these cities are going down. So it will, they will sink after few years, right? We have to minimize the glaciers to melt down. We have to stop them. So this is very interesting slide to understand that basically even if you are burning fossils, did not have the destructive power. If we can believe that, suppose burning of fuel is not having very difficult challenges, no CO2, okay, we can manage with that CO2, but still it would still be important for us to find alternatives. Still we require it, because as I mentioned that after a few tens of years or hundreds of years, all coal oil will be finishing, all fossil will finish. Then what we'll do? We need to have a renewable energy, right? Then although fossil fuels are technically renewable, we feel that they're technically renewable, but why they are renewable? Because they have been formed from the living organisms, because we put the living organism under the earth and we stay for millions of years and we get the energy, right? Problems. These are the man-made problems where in the power generation we need a power, we need the industry, we need a transport, we need a buildings, right? All these are necessities and we are using all the fossil fuels, right? So if we are using the fossil, definitely there is a carbon dioxide emission. Then how we can incorporate renewable energy sources into all these 4 sectors? So looking at all the scenario and everything, this is how reference line and RE map, renewable energy map, we have to see that. But when we mix the renewable energy, while mixing of options various, renewable energy can play an important role in all the sectors. So we have to introduce renewable sources into these all sectors so that we can minimize the usage of the fossil. So what is the idea? The technology needs for the energy sector CO2 emission reductions in 2050 compared to baseline. So idea is that by 2050, we have to reduce CO2 at a much lower. So if I bring the power sector up to this, right, we are completely using the renewable energy sources. We are very few percent of we can use a fossil, but the rest of the energy can be received by the renewable energy. Means the energy sector has the power to minimize the CO2 reduction overall. So we can focus in the power, for the power generation, electricity, automobiles, and so on. So if once you introduce the renewable energy into that automobile and especially in the energy sector, definitely all these problems will be solved. Okay. So these are 3 very important sectors where we can minimize, and among that, the power is the one where there is a possibility to reduce more than 90% of the CO2 emission. Okay, so then we have other alternatives out of the renewable energy sources. As we know that wind energy, solar energy, oceanic energy. Oceanic energy can include wave, tides, ocean thermal, and so on. Hydropower is another one. Technically it is again depend on, these are the site specific. It depends upon the presence of the rain and the water and so on, geothermal as well, biomass, and another thing is the hydrogen, which is very important. We are asking the question, how the hydrogen is important, how the hydrogen, when we employ this hydrogen into the fuel cell, how it is important, how we can use this hydrogen as a fuel. Now, if I compare this hydrogen energy with respect to the gasoline may include the petrol and the diesel and so on, and lead acid battery, you can see that energy density. What is energy density? Is a kilowatt hour. It is the energy per kilogram. So if I take the 1 kilogram of the hydrogen, how much energy I can get? So if I burn hydrogen, 1 kilogram of the hydrogen, I can get 38 kilowatt hour of the energy. On the other hand, gasoline gives the 14 kilowatt hour for 1 kilogram of the gasoline. Whereas the lead acid battery gives you just 0.04 kilowatt hour per kilogram of the lead acid battery. So you can see that still in every home we have the UPS, the inverters, all are based on the lead acid batteries. So still we are dependent on the all fossil or all old technology, which has the energy density much lower than the hydrogen. So how many times it is higher? So there is a possibility that hydrogen can be employed as a fuel for the new or renewable energy facilities. Okay. So how this hydrogen can be used? Whether the fuel cell can be an option? Would fuel cell be an option? Direct energy conversion without combustion provides high efficiency, negligible emissions from domestic and renewable energy source. What it says? It says that when you take any in a conventional combustion automobile system, you have to convert the chemical energy into the thermal energy, and thermal into the mechanical, and mechanical to electrical energy. You can see that you have a bike, you are putting like petrol in the form of chemical, it forms the thermal energy, it burns right into the combustion machine, that in an engine it burns. Once it burns, it produces the thermal energy, and this thermal energy gives you the mechanical energy, means it is producing some armature to move, and once armature is moved, you can convert it to the electrical energy, so that it's a very long process, so that the efficiency is less than 30%. Whereas if I use the fuel cell or the hydrogen, I can convert this chemical energy as in the form of the hydrogen directly into the electrical energy, right? So the fuel cell extracts energy from the fuel, and we can increase the efficiency from 40 to 70%. Then theoretically, we have the promise that we can convert this hydrogen into the electricity directly without using the thermal energy, converting to thermal energy and the mechanical energy, and finally into the electrical. So we have a promise by the fuel cell that the fuel cell can convert the chemical energy directly into the electrical energy by giving almost 40 to 70% of the efficiency. So there are several types of the fuel cells, as we know that, right? So what are these fuel cells? So there are distinctly the polymer electrolyte fuel cell, membrane fuel cell, alkaline fuel cell, phosphoric acid fuel cell, molten carbonate fuel cell, solid oxide fuel cell, and MOFC. There are a few more also. How they are classified? They have classified based on the electrolyte, operating temperature, and what is your power required. Basically, polymer electrolyte membrane fuel cell uses perchlorosulfonic acid, and which works in the range of 50 to 100 degrees centigrade, and you can get the power up to 1 kilowatt to 100 kilowatt. Okay, this is the requirement. Same way, alkaline, it has a similar temperature range, and you can go up to 10 to 100 kilowatt. There is some problem in this, because there is a small impurity can deteriorate the electrolyte, and you can we don't have any fuel cell which is alkaline in nature. It's very difficult to maintain it. Then phosphoric acid, molten carbonate, all this depend upon the temperature, what temperature you are going to use it, and how much power is required. If you go for high temperature fuel cells, you can expect more output or more power from the you can say solid oxide fuel cell gives you almost 1 kilowatt to 2 megawatt. Very high power can be expected from the SOFCs. Okay, so these are completely depend upon what is your requirement, how much power is required. Okay, so here in our studies we are focusing into low temperature fuel cells, especially low means below 100 degrees centigrade. So these are the polymer electrolyte membrane fuel cell, alkaline fuel cell, and direct methanol fuel cell also. So they are having a low power also, and below 100 kilowatt. So I will explain the mechanism of the basic polymer electron membrane fuel cell, what it is actually. And here the construction is like that. One side anode you have, another side a cathode, and the center you have a polyelectrolyte membrane. It's a proton exchange membrane. It's the Nafion membrane which conducts only proton. That's why we call proton exchange membrane. Here we bubble hydrogen gas at the anode, okay, and here the catalyst is kept. This side also catalyst is kept, and in presence of the catalyst, hydrogen get oxidized, and this once oxidation of the hydrogen occurs, this you can see that yellow is green is actually a proton. It forms a proton and one electron. So the electron goes into the outer circuit, comes to the cathode side, and proton transfer or diffuses through this membrane and comes toward the cathode. So at cathode side, the electron from the outer circuit, and from the inner side, this proton conduction with the oxygen comes here and it forms the water, right? We get the pure water, nothing else, no carbon is formed during this process. So overall reaction is completed by here the electron flows, here the proton moves, and overall circuit is closed, and we can expect some potential to be developed, and some current is flow because the electron is moving means there is a electricity is forming. So it's simple reaction, oxidation of the hydrogen and reduction of the oxygen. So overall reaction becomes, right, 2H2 plus O2 plus gives rise to 2 molecules of the water plus generation of the electricity is in the form of the potential. So this is simple construction of polymer membrane, polyelectrolyte membrane fuel cell. Okay. So what is fuel cell basically? Fuel cell is a device that converts chemical energy into electrical energy, water, and heat through the electrochemical reactions. These are the electrochemical reactions where there is a exchange of electron. So once the exchange of electron is done and the electron is detected in the outer circuit, we can generate the electricity. So there are several components of the fuel cell, especially anode, cathode, membrane, catalyst, and bipolar plates, and so on. So when you want a more number of, like a large number of the potential, you can connect all this single cell into the series, in series. If you want more current, you can stack these, one over another, so you can generate a high current. So it depending upon your requirement, whether you need a high current application or high potential applications, you have to construct the fuel cell. Okay. So as I should not forget to mention that this fuel cell technology is not a new one. It's quite old. In 19th century itself, like 1839, William Grove constructed the first fuel cell, and it was first the commercial application was done in the supercraft of the project Gemini in 1960s. You can see that in 1960 itself we have used it. Okay. But now there are a lot of research being done on this, and we have so much, sophisticated fuel cells are available in the market as well. So before again, this is a little fundamental to understand, especially you are master students, and you need to know that what is actually thermodynamics behind this, how this reaction gives you or perform and gives you the output. So we have to understand the energy conversion efficiency. What is the energy conversion efficiency of the fuel cell for an automobile, right? Like car or any bike or something. So we calculate the overall efficiency by using the tank to the wheel. Tank means we are putting a petrol or diesel into the tank and we are measuring the efficiency up to the wheel. So if you calculate this thermodynamic efficiency of current automobiles, right, it gives you 13%, just 13%. It means that almost 87% of the fuel is being wasted. It's of no use, right? Such technologies of less use, and 87% is like entropy generation, heat, and other things will happen, and we are burning the CO2. We are making the CO2 or carbon monoxide into the atmosphere. That is what. If you go for hybrid engines, right, electric plus this petrol or diesel based, in that case, the efficiency can be increased up to 35%. It means roughly 2 to 3 times higher than the current automobiles. Whereas if you fix the fuel cell to the automobile and you run the vehicle by using the fuel cell at 0.9 volt, if I mention it, I can go up to 83% of the efficiency, almost 6 times higher than the current automobiles. How does it, and how do we calculate this? Simple reaction, as I mentioned in my previous slide, is the hydrogen reacts with the oxygen, forms water, and if you deduce the gives free energy, change of this process is basically delta H minus T delta S. This is unavailable energy, wasted energy in the form of entropy. And we know that the delta G of this process is 237.2 minus is a kilojoules per mole. Delta H is of this reaction is minus 285.8 kilojoules per mole. So this by using the expression NF equal to minus delta G, we can we can determine the E max is equal to delta G by 2F. Why 2F? Is 2 is the number of electrons. Here the 2 number of electrons are taking place. Is equal to 1.23 volt. So this is how much we can expect the theoretical equilibrium potential by constructing two electrodes, anode and cathode. One side you are bubbling hydrogen, another side you are bubbling oxygen. You can expect the potential of 1.23 in a single cell. Right. If you need a more potential, you can put all these cells in a series way, and you can increase the potential. Then how to determine the efficiency? You know that the simple expression is gives free energy divided by the total heat content of the react process. It's given by delta G by delta is equal to 83%, as I mentioned. If I consider there is a heat of evaporation, the maximum heat conversion can be eta is equal to 98.5%. So still there can be a promise that thermodynamically this fuel cell shows a lot of promise for conversion of a chemical into the electricity without contributing a carbon into the atmosphere. So the pollution will be very, very low, right? This is about all basics. Again, as I mentioned that I will be talking about the low temperature fuel cells. These are the two different types of the fuel cell, polymer electric membrane fuel cell, and second one is the direct methanol fuel cell. So here anodic reactions are quite different. Here in anode, hydrogen oxidation is occurring. Here anodic is the methanol oxidation occurring, but the cathodic reactions are same. These are oxygen reduction reaction, right? So we are going to study these cathodic reactions in more detail because cathodic reactions are very, very slow in nature. They are very slow. Okay, so one has to understand the kinetics of such oxygen reduction reaction in different way. And once we increase the kinetics of this process, we will be successful. I will be talking about what are the challenges and what is this oxygen reduction. Most of my talk will be in terms of the oxygen reduction reaction only. Okay, so the simple reaction looks to be like a hydrogen reacts with oxygen. This is something I'm little discussing about electrochemistry because you are a master students. Then I have introduced these two slides, three slides, so that you can understand what is the electrochemistry behind the fuel cell. Okay, so now, as I mentioned that it's a simple reaction between the hydrogen where hydrogen reacts with the oxygen, forms the water. So what is the reaction basically? Hydrogen oxidizes, gives one electron from both the hydrogen. It reacts with the oxygen molecule, one half oxygen molecule, and forms the water. But this reaction looks very simple, but how to extract the energy is not so simple to understand. So again, I consider the reaction, reaction, how the reaction works here. You can see this reaction is basically 2H2 plus O2. Okay, rather than writing for the half O2, I will write the O2 completely and 2 molecules of the hydrogen I will take, but the ratio will be similar. So what happens if you consider the hydrogen in initial case in hydrogen molecule, the oxidation state of the hydrogen is 0. It oxidizes when you go for water side. So what is the oxidation state of hydrogen in water is +1. So hydrogen is getting +1 means oxidizing or oxidation is occurring, right? 0 to 1. On the other hand, if you consider the oxygen, it is 0 again. O2 oxidation state of the oxygen in O2 is 0. When you see in a case of water, it becomes -2 because if hydrogen is +1, 2 plus means 2. To compensate this, it becomes -2. So here 0 to minus 2 becomes negative, is a reduction. So hydrogen is oxidizing, oxygen is reducing. So it's a redox reaction, oxidation, redox reaction, reduction reaction. So total reaction is a redox reaction. So we can consider this reaction in to both conditions, acidic as well as the alkaline condition, because as I mentioned that we have polymer electrolyte fuel cell which works in the acidic media. The alkaline fuel cell works in an alkaline medium. So we'll study what happens in acidic media. We'll take an example of acidic means sulfuric acid or perchloric acid. So two different reactions can be imagined. First one, you always, as per the convention, we should write this expression in terms of the reduction reaction. When you're writing any oxidation reaction in terms of the reduction type, then because hydrogen is oxidizing, but the H2 is coming to the right hand side. Whenever H2 comes on the right hand side, it means that hydrogen is oxidizing. If oxygen comes to the left hand side, it means that oxygen reducing. Okay, it's a concept. So here I'm writing this reaction in terms of the reduction reaction. 2H plus 2 electrons gives rise to H2 and the potential becomes 0. You know that standard redox potential of the hydrogen is 0. Another reaction we have 2H2 plus 2 electrons give rise to H2 plus 2 OH minus. So which one we can select this? So you can see that since we are doing the reaction in acidic media, we have only protons. We cannot have hydroxyl ions, no OH minus. So this reaction, second reaction, we can scrap it. So only we can select this 2H plus 2 electrons gives rise to H2 and the potential becomes 0. Second one, to the left hand side, what is the reaction is happening? We are bubbling oxygen. So again, these reactions are written in terms of the reduction potential, where I mentioned that whenever O2 comes to the left hand side, and this is called the reduction reaction, right? Oxygen is reducing, right? So here 4 different types of the reactions can be written. O2 plus 4H plus 4 electrons gives us to H2O. O2 plus 2H2O plus 4 electrons gives us to 4 OH minus ions. O2 plus 2H plus 2 electrons gives us to peroxide. O2 plus H2O plus 2 electrons gives us to HO2 minus plus OH. So all possible reactions can be written. Now you can see the survey how we can find out which is the actual reaction happening here in acidic medium. So here, first reaction, you can see that the protonic condition is acidic condition. O2 is reducing, you get 1.23 volt. Okay. Second one reaction, if you go there, in this stage, we cannot afford to have the hydroxyl ions. So here hydroxyl ions are forming, which is against that we are having the electrolyte acidic condition. So this second reaction we can scrap. Third reaction looks to be in a proton formation, in protonic condition. It is okay, but what happens is that this H2O2, this entity or this moiety is a peroxide which is unstable. The oxidation of this H2O2 is more favorable. So reverse reaction is more easy favorable than the forward reaction. So that is an unstable reaction, right? Is unstable, so we should not consider this. The similar way here also the hydroxyl ion formation, we cannot accept this reaction. So the fourth, third, and second, third, and fourth we cannot accept. Only the first can accept. So this first from left RHS and first from the LHS we can consider. We can couple this reaction. You can see that H2 plus 2H plus 2 electrons. These 2 electrons will be taken here. O2 plus 4H plus 4 electrons gives us to H2O, and eventually you will have a ER minus E0. 1.23 minus 0 becomes 1.23 volt. This is how the potential of a given reaction in a given condition can be calculated. Similar way we have the alkaline condition. From this we can see that 2 types of the reactions can be considered here. 2H plus is considered, but this is not expected or accepted because in alkaline condition means OH ion. So this reaction can be expected, right? 2H2O plus 2 electrons gives rise to H2 plus 2 OH minus. Right? The second reaction can be accepted. In a similar way here in alkaline condition, first can be rejected because protons are there. In second can be accepted. Why? O2 reduces in presence of water and hydroxyls are forming, which is accepted because in alkaline condition. And again, third and fourth are generating the peroxide, where here the oxygen has a -1 oxidation state, which is unstable in nature. So reverse reaction is more favorable. Similarly here, O2 minus is -1 charge, so it is unstable. So the second reaction then can be coupled where the potential is 0.4. So 0.4 minus -0.83 becomes again 1.23 volts. So this in alkaline condition also you get 1.23. So regardless of the condition of a pH or the electrolyte, if you are using hydrogen and oxygen, you should expect the same potential, right? What I change here? Only I change the electrolyte, but the fuel and oxidant are same, H2 and O2. So the gradient is same, so you should have a same potential. So either you take in acidic condition or alkaline condition, we definitely will get the potential same, regardless of what pH or what electrolyte we use. Okay, this is all about the basics of the electrochemistry in a fuel cell. Okay, so now I told everything about the basics and all. Then you might ask where if this is the 1960 we started the first commercial application of the fuel cell, then what is the status right now? This is the status. So this first commercial car was established by the Toyota in just 5 years back. Okay, so it's a completely commercial car. It's not on lease or not on rent. Okay, so in one filling, right, it refuels, it takes 3 minutes. Means refilling means you have to fill the hydrogen. You don't have to fill the oxygen. Oxygen can be taken from the air, but here you need to fill the hydrogen. You need to have a tank, hydrogen tank, right? So it runs almost 400 kilometers or 312 miles per filling. So this is a very interesting car. And again, this Mirai, we call the car's name is the Mirai, which is the first fuel cell car offered for sale, not on just lease. So other companies also, Honda and Hyundai, they also started cars, but they were on the lease. But this car, but still you have to wait for a long, because there is a waiting list. Almost 2 to 3 years it required that you will get this car. But still we are facing some problems, and I will tell what are those problems. And this is another 2 years back, this train, which is completely based on the fuel cell and the hydrogen. We call that train as a Cordia Islet. So this is launched by Alstom, okay, the France company. This Cordia Island, the world's first hydrogen-powered passenger train, was launched in September 2018, just 2 years back. So this is almost, I guess, by the end of this, 2021 or 2022, almost 20 trains can be, will be running into the Europe, like France and Germany. Okay, it was developed by the Alstom. It is running in Germany and developed by the Alstom, which is a French company. And which is a recent, again, development in the fuel cell technology. Is the world's first fuel cell heavy-duty truck made by the Hyundai. We call Excind fuel cell. Heads to Europe for the commercial. You can see that almost 7 large hydrogen tanks. Total amount of the hydrogen is 32 kilograms. Okay, it runs up to 400 kilometers. So this is a really important. Normally, what was the doubts for the fuel cell? It cannot have a very large power or something. But now this we are running with the trucks and the trains. It means that it has a promise and it is not giving any pollution into the atmosphere. Okay, so this is a real application and very important and a distinct application of this fuel cell is assigned to fuel cell heavy duty truck developed by the Hyundai. So how to do that? How to deal with that? All this, all technology, everything is dependent upon the rate of reaction, which is given in the black curve. This black curve gives you the current technology. This gives you the current technology status. If you take this technology, the reaction rate up to this 10 times. So if I take this curve up to this blue type, then definitely this technology will be affordable to a common person. Right? Means certain researches have to be done. It means that the PFC, polypeptide membrane fuels in future, how to predict it. If I take this kinetics of this process up to this. If the reaction rate looks like this 10 times, then definitely we can afford the technology. All common people can afford this technology. So how to go ahead with that? So one important thing is that when any chemical reaction, this already you have studied in your undergraduate courses, and so that this is a potential energy diagram of the activation energy. You have studied different theories, collision theory, activation, complex theory, and so on. So the reactant to form the product, it goes to it has to cross to a activation barrier. Okay. Without catalyst. Now, when you add a certain foreign material, which call it as a catalyst, then definitely this activation barrier goes down, right? So the catalyst, how to define the catalyst? It is a chemical which doesn't take part in the chemical reaction, but activates or accelerates the rate of the reaction, right? Therefore, when you get the lower activation barrier, means you accelerate the reaction, the catalyst becomes very, very unavoidable part of any chemical reactions. Nowadays, the catalytic research is much boom, on the boom. So it is a very, very must material for many chemical reactions. So how to choose this catalyst becomes a very important point of discussion. Now we have to see that when the catalyst, we are discussing about the catalyst, is very important to know about the periodic table. And we have just celebrated 2019 as the International Year of the Periodic Table, which was developed 150 years back by Dmitry Mendeleev. Now we have to thank Mr. Mendeleev for developing such a table which gives a better classification of the different elements in the periodic table. That's why we just celebrated 2019 as the International Year of the Periodic Table, because we completed 150 years of this periodic table. Now, why I'm showing this periodic table? Just to understand that you can see that the series of these elements, copper, sulfur, carbon, gold, silver, iron, tin, antimony, mercury. Do you know when they discovered? Actually, some of these, we don't know the dates, but almost 10,000 years back. So these metals are available with the human just 10,000 years back. Even we don't know. The dates are approximate. So it means that before even knowing anything, we had metals. So we knew this, chemistry of the metals, right? How these metals came into the picture and how we understand. And apart from that, this you can see that carbon becomes very important. Gold, it becomes like ornament. Copper, this becomes very important. So point of that is that carbon becomes very important. As I mentioned, that carbon is a very, very problem in the atmosphere. When it is in the atmosphere, when it is a form of the particle, when it becomes gaseous state. So carbon becomes very, very dangerous and problematic for the human being to stay alive. But at the same time, I should not forget to mention that we need to have a carbon as well. We need a carbon. Without carbon, we cannot exist, right? In our body also, our body is also made up of the carbon and many other elements. So carbon is also must. So how to utilize the carbon as well? How to use smartly this carbon without burning. Once it burns, it's a problem. And apart from another element we are interested to study is the platinum. So platinum, we know that is a noble material, and one of the noble materials in the periodic table and in existence. So there are several properties of platinum. What are these properties of the platinum? We can know that platinum is having high work function, almost 4.6 electron volt. It has the ability to catalyze the reduction of the oxygen. It has a good resistance to corrosion and dissolution. It rarely dissolves. Very poorly dissolved into the acid or electron condition. It has very high exchange current density as well. Now, as I mentioned that when you are going to use such elements into the fuel cell, we are going to use as them as the electrochemistry. That's why we call these electrocatalysts. So these are not simple catalysts, these are the electrocatalysts where there is an electron exchange is happening. So what should be the essential criteria for choosing an electrocatalyst? So the electrocatalyst should have high oxygen absorption capacity. It should have a high structural stability during oxygen adsorption and reduction. It should be stable in the electrolyte medium. It should have ability to decompose the peroxide. As I mentioned, that peroxide is a deleterious because in -1 state it is unstable. It destabilizes other materials also, like membranes and carbon-carbon bond. It breaks, so it is not good for the application. It should be very highly conducting material. It should have a tolerance to the methanol because methanol corrodes the surface of many active materials like platinum, gold, and so on. It forms CO. It should have a low cost, right? Cost should be very low so that we can afford the technology as well. So the noble metals like platinum, platinum alloys, platinum Fe, platinum cobalt, platinum nickel, platinum chromium, platinum palladium, platinum, gold, platinum have been used for fuel cell applications and so on. But right now in the commercial fuel cell applications, we are using strictly platinum. There is no other material, only platinum. So eventually we have to face the problem. What are the problems? What are the challenges in the PMFC technology? Though we have the train, we have the bus, we have the cars, we have now the trucks also. So all these applications are existing in that in the world. But challenge is that we have very basic problems. Is that these have still over potential because platinum also gives a basic condition of the over potential. It means that during this process, during the starting of the reaction, it requires a little higher activation barrier to cross it to start the reaction. That's why the over potential is very, very high. And the kinetics is very, very slow. Or this is very, very important that the oxygen reduction reaction is a very poor kinetics. So the reaction is not so easy to happen. The cost of the platinum is very high. And the polymer membrane also very costly, which is a monopoly of the DuPont. So one has to find out the alternative for this Nafion electrolyte, the cost of the hydrogen. So hydrogen production right now is actually a byproduct of many industrial waste. So there is no actually green way of production of the hydrogen in a bulk way. We produce from the photo and all. There are some methods available for production of the hydrogen. But again, the storage is another problem. We cannot store the hydrogen in anything because it's a highly flammable gas. Polymer membrane stability and its activity matters a lot for the durability of the process. So all these things becomes very important factors when we are studying the overall performance of a fuel cell. So this is a typical IV curve of a fuel cell where you can see that this should be ideal curve where we can expect 1.23 volt is the voltage of a fuel cell. But what happens in actual case, this curve looks like this. There's a lot of losses and eventually the voltage becomes very, very less, almost less than 0.4. Then once it becomes less than 0.4, it's of no use. So there are several losses. So there are three regions: first region, second region, third region. So the first region is called the activation barrier or activation over potential because of the poor reaction kinetics. Second one is the ohmic losses because there are so many things happening in a fuel cell. They create the ohmic losses. And final one, because of the gas transport, there will be a gradient in the concentration that we call the region of the concentration over potential. So this is happening because of the flow of the gases. So eventually you will not get the potential what we expected 1.23. So what do we get here? So the E cell, which is not actually 1.23, irreversible is 1.23. So minus, these are the losses we are getting, the electronic ohmic losses, HOR over potential, ORR potential, the relative humidity because of the hydrogen transport, relative humidity because of the gas transport, and so on. And because of these all losses, we end up with the almost less than 0.4 or something. Then it becomes waste technology to be used. So everybody has to work on all areas. So when you start working on every part of this fuel cell, then one day you can achieve at least 1 volt. If you achieve at 0.8 to 1 volt constantly for several hundreds or thousands of hours, then this technology will be affordable for a common person. So apart from that, there are several challenges from the polyolefin membranes and factors limiting the PMFC performance. So what is the dependence of the water for its conductivity, which is very important. It is a high fuel permeability or crossover matters a lot. tendency to get disintegrated by hydroxyl ion. I said that this hydroxyl radical will be formed because of the peroxide formation. Once the peroxide forms in the during the oxygen reduction, those peroxide form some radicals, and that radicals will attack on the polyolefin membrane, so that the polyolefin membrane will be degrading. Okay. So, and finally, the lower thermal, mechanical and chemical stability at various operating conditions. If the polyolefin membrane, which is the heart of the fuel cell, is not stable thermally as well as mechanically and chemically, then such membranes will be of no use, and we will suffer with the loss of its power or energy density. So this is all about background of the fuel cell. And one more thing before going into the testing of the fuel cell, this is what domestic way in the laboratory we test any platinum surface. This is a typical cyclic voltammogram. I know the cyclic voltammogram means in masters you have this topic of the cyclic voltammetry. You are changing the potential from V1 to V2 or E1 to E2, again coming back to the E2 to E1. You are completing a cycle. So this is the typical nature of the platinum surface, polyelectron platinum surface. So you can see that on a platinum surface, there are the sites where you can see that there is hydrogen absorption is happening. This is a hydrogen absorption. This is a hydrogen desorption. Here platinum O or platinum OH formation peaks are seen, and here PTO reduction peak can be seen. So these can be used to understand the activity of the PTO reduction. So oxygen reduction reactions. So how to do that? We can do it by using the rotating disk electrode. We can rotate the electrode to minimize the diffusion limitations of the process, and we can mimic this reaction with respect to the fuel cell, actual fuel cell stack. Okay. So these are the preliminary reactions we do at the laboratories to understand that. So this you can construct in your laboratory to understand. Even you can set such experiment into the laboratory to understand the oxygen reduction reaction. You can study this. This is very simple, and in master degree it is very important to set such experiments. So this I will not study. So overall, what I mean to say is show that here in a catalyst we have platinum nanoparticles on the carbon support. Carbon is acting as a support, which is a very high surface area, almost 1,000 meters square per gram. On that, we have several nanoparticles of the platinum, which are acting as a catalyst. But during the reaction or during the operating condition of the fuel cell, what happens? There are several reactions happen. First one, like carbon also gets corroded. Carbon get hydrolyzed to form the CO2 plus proton and electrons goes out. So much below potential, this CO2 is forming means this carbon support itself is not stable. If the carbon support is not stable, then platinum also will be dissolving out along with the carbon. If platinum is remaining stable, but carbon itself is going out, so carbon leaches out, platinum also will go, so it will cost more. So what is the problem? Carbon dissolution is one problem. Second one, the oxidation of the platinum. This oxidation means corrosion of the platinum takes place because there are some formation of some ionic sites or permanent bonds will form with the carbon monoxide or some hydroxyl ions will form. Those platinum is of no use. Okay, this reaction, we need to have this reaction, O2 plus 4H plus 4 electrons to form the water. This 4 electron transfer reaction should happen. But during the course of reaction, course of operation of a fuel cell, all these reactions will happen. This poisoning of the platinum will happen. Ionization of the platinum will happen. Some of the particles get mixed with another particles to form a bigger particles. These are called Ostwald ripening or coalescence. Migration will occur, and so that the activity of such catalyst will go down. So our idea is to develop such a catalyst which is very, very stable in nature and which can operate for a longer time. So we what is the research then? We have to avoid such all reactions. If you avoid such reactions, you will publish the papers. That's all overall the research. So what are the different forms of the materials available to do this? These are very cutting edge, or these are the frontier materials what researchers are studying. The first one is a graphene, which is a single layer of a graphite, which is highly conducting. which is a current study. People are studying in a very rigorous way. HBN, I feel this is very important material. I'm working in a very rigorous manner, where HBN means hexagonal boron nitride. The way how graphene is formed with the different like all carbon atoms with the sp2 hybridization. Here, alternate we have boron and nitrogen. Okay, but this material is insulating in nature. Almost 6 electron volt is a band gap. So it's insulating, but in our laboratory, we are controlling the band gap of such boron nitride. Another area of current research is metal organic frameworks. These are the frameworks made up of metal as well as the organic chains. Carbon nanotubes. This in 1980s, 85, Small and Proto, they started, they discovered this, they got a Nobel Prize as well. But still this ENT is being a very interesting material, which is a tubular graphene sheets. MOS2 is a sulfide, it comes in the chalcogenide group. Then C60 is a fullerene, where you have a Buckminster fullerene kind of structure of the carbon. We always call it the third allotrope of the carbon. And MAXins, which is, budding area of the research. We are studying the chemistry of the MAXin, where we have the metal transition metal and third group element, and we have the nitride and carbides. All these two-dimensional carbides and nitrides can be considered under the MAXins or MXins we call, and platinum nanoparticles are different metal nanoparticles. These are all functional. These are the functional materials which can be used to control their reactions and reaction kinetics as well. So our idea of our, my laboratory is to, the objective of our group is to, to generate or to design a high performance PMFC, polymer electrolyte membrane fuel cell and alkaline fuel cell. By studying different way, we have to first design a hybrid materials for fuel cell, then we optimize by modeling and DFT, then we go for morphological and structural analysis. So again, we can study their testing and everything. So it's in the loop we are working with the modeling and DFT and how to get the optimized high performance PMFC or alkaline fuel cell device. So how to do that? There are two different ways how to achieve the goal. The first one is by developing the catalyst area and developing or modification the membrane parts. In the catalyst part, we can develop such a new material, platinum-based new material, which forms a low oxygen species at high voltage. So even at high voltage, our platinum surface should not be corroded. That is the idea behind that. Okay. So in second one, we have the membranes where we can call this. These are the new proton conducting membranes, where the fast proton conduction without water or low humidity condition can be achieved. So I'm going to focus in this part only, but since the time is not there, and I will just give one or two slides why these platinum alloys are important as far as the oxygen reduction is considered. Okay. So when as I mentioned that the basic reaction is this one, electrochemical reaction. The platinum comes in contact with the oxygen, then oxygen makes a partial bond with the platinum like that. It protonizes, it forms the HOOO. Another protonation happens, like it forms a peroxide kind of linkage, OO minus. Then what happens? Then suddenly after water forms, or it has to leave the bond between this. Breaking of this OO bond is very important. Once you break this, it is an oxygen reduction. So once it breaks, then this PT-OH bond should break down and to form PT again. We should get the PT again, right? So we need a platinum problem. So when that retains there, then it creates a problem that we call it as a platinum corrosion. So how to avoid that? Then, people started adding some transition element into that, like a platinum, cobalt, and nickel, platinum, iron, and cobalt. So when they started adding that, their activity, went into increase until it reaches to 50% of this transition metal. So I take an example of the iron. You start adding the iron atom into the platinum matrix. The activity increases with the increase in the iron content. It reaches to a maximum where the iron content was 50%, atomic percent. After addition of the iron further, like 50 to 100%, then what happens? The activity decreases. Why does it happen? In initial case, the increasing donation will increase because the O2 to PT, donation is a faster one. There is no problem with the back donation. Back donation also was a very efficient and instantaneous. But when we increase the transition metal further, the back donation stops. So it means that your bonding of the PT and O should be intermediate, so that the back donation should work in an instantaneous manner to get the PT in a rejuvenated manner. So this can be possible only when we have the 50% of the transition metal and 50% of the platinum. And during that case, we formed superlattice structures. And so superlattice structure becomes very important for platinum, electrocatalysis in the fuel cell. So this again, I will not stop. So several reactions have been done. So here we have developed several superlattice structures based on the PT and different M and N. M and N are different transition metal like a manganese, iron, copper, cobalt, nickel. So we have developed like a PT, Fe, CO, where the Fe and CO are the transition metals. And you can see that when we make these superlattice structures, what we are going to do that? We can reduce the symmetry. So alternate platinum and cobalt will stack along the C-axis, and mixture of platinum and cobalt will along the A-axis. So what is the effect into that? It maximizes the tetragonality of the PTM composition. When we make the 50% of the transition metal together and the platinum, then we maximize the tetragonality. So it forms the face-centered tetragonal structures. And definitely when we have PTM and PTML kind of structures, it will affect the symmetry, and we expect the high activity and high stability. That was our idea. But when we have seen in case of this like iron containing materials, catalysts, we have seen that the very famous reaction is the Fenton's reactions. The Fenton reaction is promoted by the iron and copper when peroxide is formed. Whenever the peroxide forms, in presence of iron and copper, OH radicals form, and this OH radicals becomes very, very challenging and problematic for the electrolyte stability. So we started avoiding the iron. So then we developed PT2CON structures, and which give us a very interesting surface, and which is called the face center cubic structure of the PT2CONI, where we have a 2 PT and 1 nickel and 1 cobalt structure. Okay, so here you can see that the activity of the PT2CONI is much higher than the commercial platinum. So idea here mentioned that when I add some foreign transition element into the platinum matrix, I can increase its stability as well as the activity, and such materials can be installed or used in the device part of the fuel cell. So I will show one application here, how it works here. So when this PKK is a commercial platinum catalyst, and PT2CONI catalyst is our catalyst, you can see that when we measure their electrochemical surface area, so during different cycles, stability cycle, 10,000 cycles. So the TKK PTCM is commercial catalyst. It starts with a 46 meter square per gram, and continuous cycling, it reaches to almost 10. It's so much loss, huge loss. It's starting with the 48, it is ending with the 11 after 10,000 cycle. Whereas our PT2CONI, which is a face-centered tetragonal structure, gives you starting with the 26 and ending with the 20. So just 6 meter square per gram loss. It means that a very, very minimal loss into the ISCA after stability. It means that when I make the face-centered tetragonal structure, I will get a stable structure into the this is a device, actually this is a fuel cell measurement. I showed that, and there is a very minimal changes even after structural calculations we did. Okay, so I will not be talking about this in more details. So better, I feel that I have finished my time. I think it's more than 1.5 hour I'm talking here. So apart from that, last one point I will tell here, we have hexagonal boron nitride one. We have the idea of feeling that if I take a two layer of the boron nitride, I can make a tiny fuel cell where one side I can oxidize hydrogen so that proton can diffuse through the space provided between two rings, where the proton can be collected and oxygen reduction can happen. So two-layer boron nitride can be used as a tiny fuel cell, and that's what I should call it as a vein, inert. This EHBN is inert, is an insulator in nature, like a plastic. When it becomes active, when I modify the structure, if I make only two layers. So this is like engineering of the materials. That's why the Professor Kobayashi said that those who change the material, those can control the technology, or those can change the technology as well. So that's keeping in mind that we are working into this direction, that how this hexagonal boron nitride, which is insulating in nature, which looks like an analog of the graphene. You can say that it looks like the same, only slightly still tilting of the layers. Right, but this is sp2 highly conducting, but this is a highly insulating. So I can tailor, I can control the chemistry of this HBN to get this inert into the active material. So that is with great challenge we have, and with this I would like to stop, and I would like to thank the organizers providing me such a wonderful platform to present my work. So at the end I should talk here that hydrogen, we are developing a hydrogen train which is completely based on the hydrogen, and we are working with the integral coach factory of the Indian Railways, right? And I should end with this, the quote of manager of the exploratory research Royal Dutch Shell, Herman Cooper, that we are at the peak of the oil age, but the beginning of the hydrogen age. Anything else is an interim solution. The transition will be very messy and will take many technological paths, but the future will be hydrogen fuels. We are having so many challenges in front of us, but we are in the middle of the oil age and the hydrogen age. So the transition from the oil or coal to the hydrogen will not be smooth, but at the end we have to accept that we have to live with the hydrogen, and we have to accept the hydrogen, which gives you completely green energy technology. So this is our idea. We are going to develop a hydrogen-based train in future. So this is again a hydrogen economy, which is given by. So our aim is the objective is to save the energy, show the public how efficient fuel cell vehicles are, how emissions of CO2 gases will be reduced in future, or raise public awareness. We have to, since you are master students, we have to tell people that minimize the usage of electricity, minimize throwing, don't litter onto the road, minimize the pollution, create new sources of renewable energy, slow down the climate change, minimize the temperature, global warming. And with that, I thank you very much, organizers again, and you visit to our website. You are welcome to our laboratories. You can communicate with me with what is your interest and whatever. If you are qualifying in a CSL, examination, UGC, NET examination, you are welcome to my laboratory. I can directly accept you. Okay, thank you very much once again to the organizers. Thank you.
Thank you, Dr. Kakade, for your very nice and informative lecture on various aspects of chemistry. Surely your talk will be benefit to our participants in their academics, professional and research career. It was honor for us to have you as a resource person. We know that your time is precious, and we are grateful that you have shared some of it with us. We look forward to your participation in future events. Thank you very much.
Ladies and gentlemen, I am Sanjay Kale, Head, Department of Chemistry and Organizing Secretary of this 3 days national webinar, which hereby successfully completed within a scholarly touch due to your notable attendance and informative presentations by all the eminent speakers. I think this is not the end of our interaction with all of you, but it is a startup for making and building a bridge between scholar, academician, and scientist from research organizations. In this webinar, we put forth before you a galaxy of well-known fellow scientists who are working hard in their respective field for the benefit of society and mankind. I am sure that you all must enjoyed the valuable presentations with detailed information and experiences of their unparalleled research contributions. As per motto, we for the student, the college team, along with able leadership of Honorable Principal Dr. Chandrasekhar Murumkar, always ready to make a platform available for such type of interactions among the students, research scholars, faculties, and eminent scientists from various arenas. Due to this interaction, we have conducted this particular webinar, and for that purpose, we contacted the eminent resource personalities and requested them to interact, share their knowledge and their experiences with us. I am very much sure that all of you must be benefited certainly due to presentation of them. Dr. Sharad Lande from Reliance Industry Mumbai, who talk on industrial catalysis. Dr. Ajay Chhatre, a very good friend and classmate of mine from United Phosphorus Limited, Mumbai, presented polymorphism and its applications. Dr. Nilesh Srigadi from Harman Phenochem Limited, Mumbai, discussed on role of magnet in structural determination, that is NMR analysis. Dr. Sanjay Dabhade, our alumni from OCAD Research Center, Aurangabad, focused on drug discovery. Dr. Sudhir Arbuz from CMET Pune talk on synthesis and applications of nanostructured material. Dr. Bhalachandra Kakade from SRM Research Institute, Chennai, discussed electrocatalysis, fuel cell, fundamentals and applications. On the behalf of Anikant Education Society, Tuljaram Chaturchand College, Department of Chemistry and Organizing Committee, I am very much thankful to all the eminent speakers who shared their valuable time with us and lead this webinar towards a grand success. Secondly, the charm and essence of a webinar depends on the registered attendees. I gladly present before you that there are 345 attendees, includes PG students, research scholars, faculties and professors in the field of chemistry who took a keen interest and patiently attended all the sessions. These fellow attendees are from Pan India, which covers 15 states like Madhya Pradesh, Andhra Pradesh, Uttar Pradesh, Tamil Nadu, Kerala, Odisha, Punjab, Haryana, Gujarat, Delhi, Telangana, Manipur, West Bengal, Karnataka, and certainly from Maharashtra. I heartily extending my gratitude towards all of them who made this webinar successful. I am very much thankful towards Anikant Education Society, the Honorable Principal, Vice Principals and Departmental Organizing Committee for their valuable support and guidance during the entire event. Especially the RUSA College Coordinator, Dr. Ajit Telve, and Webinar Coordinator, Dr. Yogesh Indulkar, for their limitless cooperation. Last but not the least, I extend my gratitude towards the faculties from Computer Science Department who took care and efforts for last 3 days with their technical support. With these few words, I am concluding my talk and extend my best wishes for entire success to all of you. Thank you very much. Now, I am inviting Dr. Yogesh Indulkar for the vote of thanks. Thank you very much.
Hello everyone associated with this webinar. As all good things come to an end in life, so is the webinar. I am Dr. Yogesh Nana Indulkar, coordinator, present here to propose vote of thanks. Please note, feedback link is provided to you on your registered email, Telegram group and YouTube chat. For getting the participation certificate, filling the feedback form is mandatory. Honorable Member of Anekant Education Society, Honorable Principal of our college and convener of this webinar, Dr. Chandrasekhar V. Murumkar, respected Head of the Chemistry Department and Organizing Secretary, Professor Sanjay R. Kale, our most valued invited resource person, and dear participant, ladies and gentlemen. It's my privilege to have been asked to propose a vote of thanks on this occasion. First of all, I would like to take this opportunity to thank our Anekant Education Society and members associated with the society for providing academic freedom to students and faculties to develop the humanity. I am very much thankful to our principal for his inspiring mentorship, motivation, and enthusiastic support. I, on behalf of Organizing Committee of National Webinar on Trends and Challenges in Chemistry, extend thanks to Rashtriya Uchchatar Shiksha Abhiyan, RUSA, for sponsoring this event. I am very much thankful to Dr. Ajit Telve, RUSA coordinator of college, for continuous support, advice, which have greatly helped towards the successful organization of TCC 2021. I sincerely thank the all vice principals and registrar of the college for their valuable support and suggestion. I am also thankful to administration in general for providing us with all possible logistic support towards organizing this event. With the words, I would like to thank our distinguished speaker, Dr. Sharad Lande, Dr. Ajay Chhatre, Dr. Nilesh Srigadi, Dr. Sanjay Dabade, Dr. Sudhir Arbuj, and Dr. Bhalchandra Kakade for making excellent presentation and making the webinar interesting and meaningful. I take this opportunity to thank the technical staff, Mr. Rahul Shah and Mr. Purushottam Dikshit, for providing their valuable skill to organize this webinar on YouTube live platform. I also thank Professor Upendra Chaudhary for chairing the technical committee. I acknowledge the unwavering support and guidance received from our head of department, Professor Sanjay R. Kale, who is organizing secretary of the webinar. A special thank to the organizing committee, teaching and non-teaching staff for their unflinching support and coordination. Finally, our heartfelt thanks to all participants and our students for active participation. Again, thanks to all people who helped me either directly or indirectly to make the webinar successful. With these warm words and a kind message, we move to the end of today's seminar. Thank you very much.